So now it's time to take a look at limits from a graph. So when we work through limits from a graph, what we're trying to do is find the y value of the graph as the x value approaches whatever is notated down here. So as the x value approaches 0, what's happening on the graph is that the y values in this case are from both sides approaching the number 2. So we would say the limit is approximately 2. Moving on to the next one, we have this plus sign up here in little exponent, so x is approaching 1, and there's a plus sign. That means from the right or from above. And what they're referring to is on a number line, values to the right of 1. So I come over to the graph, and I'm coming in on the x-axis toward the number 1, and the graph is coming in here, and it looks like the y value being approached is 0. And notice that I'm writing these squigglies for approximation because we won't get exact values until we use algebra. The negative sign up in the exponent means from the left or from below. So as x is approaching 1 from below, my graph is actually up here, up here, and the y value right here is approaching 2. So I'd say approximately 2. So the next question is the limit as f of x as x approaches 1. Well, back over to the graph, when we came to 1 from above or from the right, we came in towards 0. When we came into 1 from the left or from below, we came towards 2. Those values here are not equal, and therefore we would say that this limit does not exist. And then the last question dealing with 1 is, what is f of 1? Well, f of 1 is up here, so f of 1 is approximately 2. So based on what I just taught you, I'd like you to hit pause and work through the rest of these questions, and then you can check your responses in a moment. All right, let's take a look at these problems. First of all, as x approaches 2 from the left or from below, the y value being approached is right here, it's 1. F of 2 is approximately equal to negative 1, that's right here. The limit as x approaches 2 of f of x, coming in from both sides here, is approximately 1, this y value right here where the hole is. The limit as we approach negative 3 from the right, we're coming in from the right, so we're approaching negative 1. As we approach negative 3 from the left, right here, we're also approaching negative 1. So since we're approaching the same value from the left and the right, that means our overall limit is going to be negative 1. So that what I just said was that if the left-hand limit, meaning as we approach from the left, is equal to the right-hand limit, meaning coming in from the right or above, if those two limits are equal to each other, that means that the overall limit is existent and is exactly equal to the left and the right-hand limit. In this case, f of 3 is up here, it's approximately 1. As we approach negative 4 from above, that's down here, we're going down to negative 2, and just FYI, they will not ask us about negative 4 from below since it is not in the domain of the graph, so that's not going to be a question you'll ever have to consider. As we approach negative 1 from below, that's up here, we're going to go to 1, coming in from below here, and then f of negative 1 is up here at approximately 2. So that brings me to the limit laws. And I don't want to spend a lot of time on these. I just want to point out in layman's terms what they mean. This says if you have the function f and the function g and the limits at a exist on both of them, that means that the left-hand limit and the right-hand limit must exist and be equal to each other for both the graphs f and g. If you add the graphs together or subtract them, you could add or subtract their limits. If you multiply a constant by the function, you can factor that constant out in front of the limit. If you multiply the two functions, you can multiply their limits. If you divide the functions, you can divide their limits as long as the denominator is not equal to 0. If you raise a function to the exponent n, you can also raise the limit to the exponent n. If you root to the root n, root the function, you could also root the limit, assuming that that root exists. And then these are two special limit laws that we use a lot. The limit of some constant function y equals c. So here is my graph of y equals c. The limit as x approaches a for any value on that graph is going to be that constant value c. And then this last one is actually the graph of y equals x right here. So anytime x approaches a, for any value a, the y value also equals a, so that limit equals a. I'd like you to pause the video for a moment and try problems 1 through 4 using the graphs of f and g. For number 1, I'm just evaluating the limit as x approaches -2 of f of x, which is right here at 1, plus 5 times the limit of g of x, which is -1. So then I'm just adding 1 plus 5 times -1 to get -4. With number 2, this property only works if each limit by itself exists. And what you'll see is when you look at g, as x goes to 1, we have one limit coming in from above and a different limit coming in from below. So that limit does not exist, and therefore the overall limit does not exist. For number 3, we can divide our limits only if the denominator is not equal to 0. And in this case, as x approaches 2 of the g function, that limit is 2, so we're dividing by a 0, so this limit dne. And in number 3, I'm taking the limit of g as x approaches 3, and that is 1, and then I'm squaring 1 and getting 1.